We are FTC Team 13072 Fellowship of the Robot, and this is our Control Award video. For Autonomous, the robot drives forward to a point, turns to 3 predetermined angles, knocking down the power shots. The shooter fires at a slower speed and a higher angle to hit each peg softly, preventing them from recoiling into their original position. For 0 and 1 ring routes, the robot drops the wobble goal in the correct zone, then intakes and shoots any available rings in the stack, and finally delivers the second wobble goal. For a 4-ring stack, it instead pulls back and intakes the stack, progressively firing them into the tower goal, and then delivers the wobble goal and parks on the line. These routes are supported by 2 functions: turn, which uses a highly tuned PID controller to align the robot with a desired angle, and move to, which uses dead wheel odometry units plus some advanced math to find the vector of the robot's movement, which is used to plot the robot's path. Our autonomous routes are highly configurable, allowing us to adjust them to work with other teams on the fly. Additionally, we have created a modified version of our driver control program that records the robot's positions and actions, which are saved as a series of arrays and stored in a file, which is then played back by another autonomous op mode. This allows us to create completely new routes within 15 minutes. To assist drivers in Teleop, we use a Mecanum drivetrain, allowing the robot to move in any direction. We have taken an extra step as well, using the IMU to find the robot's angle in relation to the driver station, allowing us to have field Mecanum drive, which means the driver's inputs always match the direction he is facing, rather than the robot. Additionally, the driver has triggers to adjust speed when needed. The operator has many functions to control, so a number of automations were created to aid in this process. One button can switch between the intake and fire mode in an instant, changing the ring bucket's position and changing which controls are available to the operator. In fire mode, the left trigger will fire shots individually, while the right trigger will fire repetitively on a timer in order to shoot them as quickly as possible. The robot also uses the odometry pod to calculate the correct height and wheel velocity to use for each shot, allowing it to shoot from anywhere on the field. Our robot also has an auto-aiming system that uses simple trigonometry combined with known preset locations on the grid to find an angle and aim itself at the target. In addition, to adjust for shooter mechanical error, the robot uses its distance from the target to calculate a scaling angle offset. This allows the robot to point at the target no matter where it is on the field. The operator also controls the wobble arm using the D-pad, cycling the arm through several preset positions. Once in position, the claw can be opened partially to allow the goal to slip through without fully opening and catching on the wall. During in-game, we created a predetermined mini program so the driver can line up on the field with a generous margin of error, and with a quick double button press, the robot will repeat its soft, precise shots to all 3 power shots with ease. We use several sensors to accomplish all these many tasks during the autonomous and driver-controlled periods. We use a webcam to detect the ring stack at the beginning of the match. We use a Kiwi odometry system to always know where the robot is on the field. We also use the onboard IMU to accurately determine the robot's angle in relation to the goal. We use a limit switch to help ensure the wobble claw is in its proper position. And finally, we use a LiDAR distance sensor to count how many rings enter the robot. We also use LED lights to give our driver and operator feedback. For example, the lights turn yellow when the robot is auto-aiming, and they turn purple when the wobble goal is secured. Thank you for watching our Control Award video.